Hey everyone, let's go ahead and design an online auction together today. Thanks for being a premium user. First off, what is an online auction? An online auction is a service that lets users list items for sale, and then other users can compete to purchase that item by placing increasingly higher bids until the auction ends, at which point the highest bidder wins the item. So think about eBay. This is a general auction. And then we're going to be going for not a blind auction. And so you can see the bids of other people as they're coming in so that you know that you need to bid higher. That's the system that we're going to be designing here. So we'll start with our requirements according to our delivery framework, as we always do. And we'll start with those functional requirements. The functional requirements are, of course, the features of our system. The user should be able to statements. And so the very first thing is that a user needs to be able to create an auction. And so this is basically listing an item up for auction, up for sale. Right? That's the very first thing. Next is that users should be able to bid on an auction. So they should be able to place bids on that auction. And then last but not least is that users should be able to view auction details and the bid history. And so if I open up an auction item, I should be able to see pictures of that item, the description, I should be able to know when the auction ends, I should be able to see the current maximum price, basically the history of the past bids, so that I can know maybe what I need to bid next. Now that we have the functional requirements down, the next thing that I would recommend that you do in the interview is you just ask your interviewer a little bit about scale. And so when I'm the interviewer, I hope that people do this proactively. And then I'll tell them the scale in this system would be that we have 10 million concurrent auctions at any given time. Right? So how many users? Maybe hundreds of millions of daily active users, but the interesting bit here is that there are 10 million concurrent auctions, and we can probably work backwards from what a reasonable number of bids are per auction in order to understand the total number of bids. So that's going to be the scale of our system, which allows us to then flow naturally into our non-functional requirements. There we go. And these are going to be those qualities of the system. And so this is what qualities does our system need to have in order to ensure a fantastic user experience. And so the very first thing that I would consider always is your CAP theorem. Do we need to prioritize availability or consistency in this system? Is it the case that all reads need to be reading the latest rate? And for bids, as is often the case with any kind of financial situation, we do care about strong consistency. And so we're going to write strong consistency for bids. The general idea here is that if I'm going to place a bid for $20, I need to know in the database what the current maximum bid is so I can understand whether my bid should be accepted or rejected. Because if the current maximum bid is $25 and I bid $20, then I should get a synchronous response telling me, your bid's rejected, that was too low, try to bid again, there was already a bid higher than that. It's going to be a good user experience. And so we're going to say strong consistency of bids. Now, a really quick note, some people may be thinking to themselves, is strong consistency really required? And the answer is no. There's a permutation of this problem, and we'll talk about it a little later on, in which you can satisfy the requirements without strong consistency. But when this question is asked in an interview, usually one of the things that they're most interested in is how you handle the strong consistency on bids. It's like the most foundational of the deep dives, and so we're going to keep that there as our non-functional requirement. The next thing that we want to consider is the fault tolerance of the system. And so of course every system should be fault tolerant, but in this case we're going to be specific in that we can't drop any bids. You know, a user ends up putting late in an auction maybe $1 million bid on some game-worn Messi jersey. It would be bad for us to drop that. It would be really bad for us to drop that. And so we want to have the fault tolerance on bid placements here. That's one that we'll keep an eye on in our deep dives. Another one is real-time client updates on bid history. And so I want you to imagine in this case, and this is a useful exercise to do in your design, that you're sort of closing your eyes and you're visualizing the product. And you're trying to make a decision of how much you should bid on an item. Well, in order to make that decision, you're certainly going to need to know what the current maximum highest bid is. You're going to need to know the bid history. And you're going to need that bid history to be up to date. You can imagine a situation in which you load an auction, it says the current price is 100. You think about it for a really long time, and then 5 minutes later you place a bid, but the maximum bid has already changed. If it wasn't updating in real time on your device, you wouldn't have known this. You would have had to refresh, right? And so it's going to be important for us to have real-time client updates on that bid history so you know what you need to bid in order to win. And then that last thing here, which we talked about with scale, but now we can translate that into a non-functional requirement, is that we need to be able to scale to our 10 million concurrent auctions. So we'll talk about, as we're designing our system, how we satisfy those scale requirements. So now that we have the requirements outlined, we can move on to our core entities, and then we'll go from there onto our API. And so for the core entities of this system, this is the period where we're going to outline the nouns of our system. These are almost always translate to the tables that are in your database. And so what would be our tables? What would be our core entities here? Well, of course, we're going to have some notion of an auction. Now, an auction is usually over an item. Now, this isn't strictly necessary. Many of the times when I ask this question, candidates sometimes include items, sometimes don't. And to be honest, as an interviewer, it makes no difference to me. The idea to normalize these two is that maybe you have an item for which you run an auction over and then it doesn't sell. And then a month later, you run a new auction on that same item. Right? So you could have it broken up in that way. So we'll do that. Of course, that's not a requirement from this system. These could or could not be normalized. It doesn't much matter, but we'll do it. Auctions and items. And then importantly, we'll have bids. And lastly, of course, maybe least importantly, there's always going to be a user who's creating auctions and issuing bids. Those are our core entities. We're not going to go into the data model until later in our high-level design. You absolutely could upfront at this point if you feel like you know them. By all means, get started. But we find that if it's a system that you haven't designed before, it's a lot more intuitive to kind of punt until you're later on in the design. Now, after our core entities, we go on to those APIs. And the APIs, we're going to just map nearly one-to-one in many cases from our functional requirements to an API endpoint. These are user-facing API endpoints. And so the first thing that we had was to create an auction. And so we need to create an auction. We need an endpoint for that. And so this is a creation event. We're creating a new row in our database. We're creating a resource. So it's going to be a post. And we're going to post to auctions. This is a plural noun as our resource name, and that's going to return to us the auction. And so maybe what we do here is that we pass in the item. We can create the item here, including the images and all of those things. The start date of the auction, maybe the end date of the auction, and then how about a starting price? Right? I don't want to sell my Apple Watch if it's less than $100, so I can put a starting price there. Seems like a reasonable endpoint in order to create an auction. The next one is that we need to be able to bid on an auction. And so let's add bid on auction. And so in this case, similarly, we're creating a new row. We're creating a bid. And actually, this is worth me calling out. A common mistake I see, particularly for mid-level candidates when I ask this question, is that they don't normalize bids here. They don't have a separate entity for bids. They actually just have an auction. And their assumption is that like one of the columns on here is going to be like the current bid. Generally speaking, this is a bad idea. It's a bad idea for a lot of reasons. Maybe the main one is that when it comes to actually like auditing, tracing, and understanding which bids any given user has posted, you're not going to know that. Like I as a bid want to be, or a user would want to see like what bids have I posted and which ones were accepted, won, etc. And we wouldn't have that bid history if we did it this way, which is actually one of our functional requirements. So slight aside there, you don't want to do that. You want to have bids separated. And that means that we have a separate bids resource, a separate bids table. And so we're going to post a new row to that table. And so I'm going to do post auctions on which auction, auction ID, that auction ID with a path parameter, and then slash bids. And so this is common here. This is because there's a relationship between auctions and bids. And I need to know the auction in order to place a bid. And so I'm going to make it a required path parameter. You could also put this in the body of your request. That's totally fine too. There's no right or wrong answer here, but this is pretty common in RESTful semantics. And so this might return to us the created bid, as well as whether or not it was accepted or rejected. That might be one of the properties, or will be one of the properties on our bid. And then the input here can just be the bid details, not including accepted or rejected. We don't know that yet. And so the bid details, of course, would be like the price that we're bidding. Okay, so we can create an auction, we can bid on an auction. This is going to create a new bid row for that given auction. And then we need to be able to view auction details and the bid history. And so view an auction. In this case, this is just a simple get. We're gonna have that auctions resource again. We're gonna see the auction ID. And this should return to us the auction, it should return to us the item, and then it's probably gonna return the bid. And now, depending on how many bids there are, maybe you wanna introduce some pagination here. That would be reasonable. You could even break these endpoints up such that you don't include bid here, and we have get, auctions / auction ID / bids, something like that. Not going to be the priority for this particular interview, so I'm not too worried about it. I see candidates do all the above, and I accept all the above. No worries. Now, this isn't going to satisfy our real-time nature that we talked about in our non-functional requirements. Totally fine. I might make a call out to my interviewer at this point and say, you'll notice that currently this is a single RESTful GET API, which won't satisfy our real-time requirements. I'm going to need something else, like WebSockets, SSE, or otherwise. And I'm going to talk about that in our deep dives. All right, so we've done the setup. We got our functional requirements, our non-functional requirements, our entities and our APIs, and we're ready to move on to our high-level design, where the goal of the high-level design is for us to sketch out components on a whiteboard in order to be able to satisfy all of our core functional requirements. And so, given that our APIs were derived from these functional requirements, we're going to be explicit about what happens when each of these user-facing APIs is called. At this point in your interview, you should be between 10 and 15 minutes in. 15 minutes if you're mid-level or so. If you're senior staff, you want to be shooting closer to that 10 or somewhere in between so that you leave yourself a lot of time for the most interesting stuff in this design. So far, it's just the setup. So let's get into that high-level design, starting with users creating an auction. So when they call this post auctions API endpoint, what happens? Well, they're going to call it from a client. This client is going to be your browser, web app, maybe it's an iOS, Android app, doesn't matter, anything with which they interface with your website or your app. And then that's going to go directly then to an API gateway. The API gateway, let me zoom in so this is easier. The API gateway is directly responsible for routing. It's going to take any API request and route it to the appropriate microservice. That's the main goal. But it also handles some other middleware. Importantly, when I do interviews with candidates, oftentimes they spend a lot of time explaining the API gateway to me. Don't do this. It's not the most interesting thing. It's just some routing middleware. No worries. So keep going. Don't get bogged down there, and focus on the things that are a bit more interesting. And so we're going to create our first microservice. This is going to be our auction service. And so when a user calls that create auction, it's going to come to our auction service. And then we're just going to create a new row in our database for that auction and that item respectively. And so now we can start to talk about the actual columns in our tables, the actual data model. You're going to have an ID for an auction. You're going to have a foreign key to an item. You're going to have that start time, an end time, the creator ID, foreign key to a user, and a starting price. And then maybe you have some other things, but those are the most important. And then we talked about normalizing item. So you'll have an ID for that item, you'll have a name, you'll have a description. Maybe you'll have some, image links off to S3 or something. I'm not even going to draw that part because it's just not the most interesting part of this design, and I don't want to get distracted. So at this point, if a user were to hit the API request to create an auction, that data is going to flow to our API gateway. It's going to route it to our auction service. Our auction service is then going to issue a write request to our database to create two new rows, an auction and an item, respectively. In the case the item already existed, of course, then we would just be creating the auction. But we're not going to get too into detail in those corner cases because this is just the high-level design. We want to keep moving so we can get to the interesting things. Now, the next part of the high-level design is that users should be able to bid on auctions. And so this is what happens when somebody posts this bid endpoint. And so the first thing that I'm going to do is I'm going to add an additional microservice here. I get the question oftentimes, how do you know when to separate services? The reality is in production environments, you're going to make this decision based on a number of factors. Factors even including the different teams that are working on them, the different hardware required for each of these respectively. In a system design interview, typically the rule of thumb can just be that when there's enough of a difference in their read or write throughput respectively, then it might make sense separating, especially if this is operating at scale. So in our case, I'm expecting that there's going to be a lot more bid rights than there are auction service rights. Let me increase my spelling since I just saw that, improve my spelling. So I'm going to separate them, and that's going to allow us to later scale these independently. Maybe we can have a lot of these when we have fewer of those, or we put this on better hardware and it's optimized for the right throughput. These are the sorts of discussions here. And so if a create bid comes in, it's going to hit our bid service, and then we're going to go write that bid to our database. And for that, we're going to have a new bid table. And this bid table is going to be ID, a foreign key to our auction ID. What else do we want? The price of the bid, of course, a foreign key to the user ID who posted the bid, the time this bid was created, and then maybe importantly, a status. Was this bid accepted or was it rejected? In other words, at the time it was placed, was it the highest bid or not? Now, in order to determine that, we would query all of the current bids, determine if it's the highest one, and then write accepted or rejected. There's actually some complicated synchronization issues here, and that's one of the things that we're going to talk about when it comes to consistency in our first deep dive. But for now, for the high-level design, this is what's going to happen. I would probably call this out to my interviewer. Like, I know that I'm going to have some issues here, actually. And so you could either talk about them right away up front if you already know the solution. Alternatively, in writing this, it might come to your mind that there might be a problem here. And so you might even spell it out, like I'm going to come back and consistency issue, and tell your interviewer I'm going to come back and I'm going to work on that. Now, I'm writing bids to the same table as auctions. Is that okay? Is it not okay? This is a question we get a lot. Of course it's okay. And so there are some beliefs that every single microservice should write to its own database. This is to handle things like fault tolerance. If one goes down, you don't break everything else. This is a good idea. It's by no means a bad idea. But it also means that in places where you need transactions or you have relations between data, you kind of break those relations, and these transactions then become distributed. And so as you're going to see later on in our design, and as you already see now, there are strong relations between each of these things. And we're going to issue transactions. If you don't know what I mean there, don't worry, we're going to get in the deep dives in the auctions and bid table. And so having them thus in the same database is a necessity, or else we wouldn't be able to do this. And so in this case, I'm choosing a single database. As you can tell based on the fact that I'm talking about relations and transactions, I'm going to choose an ACID database. And so our favorite go-to ACID database is going to be Postgres, so maybe I'll make that decision now, but I'll further justify that when we talk about consistency in our deep dives. But taking a step back, a bid came in, we got to the bid service maybe queried the database to say, hey, what's the current maximum bid on this auction? We returned that to the bid service, and then the bid service wrote to the database with whether or not, with this new bid and whether or not it was the highest or not, thus accepted or rejected. So there we are, high-level design, plenty of flaws, we're going to fix them. The third is the functional requirement of the view auction details or bid history. And so for this one, the really simple thing that we could do is just have the client issue a get auction request here. And then that get auction request is going to go to our auction service and get details about the auction. And so similarly to how I was talking about in the API, maybe this is two API endpoints, also get bids for an auction ID like we sketched out. Call these in parallel, get both of them. That's probably what I would do, to be honest. But it would also be fine if it was just the one. And like I said, it's not the most interesting part of this design, so it doesn't really, it's not something you would emphasize in your system design interview. But nonetheless, the user is going to issue a request, whether it's one API or two simultaneously APIs. We're going to query our database, and we're going to return to them information about the auction items, and the past bids that have been placed on that auction so that we can render that on the client so that they know everything that they need to know in order to make a decision as to whether or not they would bid. Again, I might call out to my interviewer, like we talked about earlier, that this isn't going to be real-time enough. This isn't going to satisfy if a user is sitting on this page for 5 minutes and the bids have changed. And so that's something that I would inform them. We're going to talk about that soon in our deep dives. But for now, here's my very simple high-level design. It's my foundation for which I can build the rest of my design on as we expand to deep dives, ensuring that we meet our non-functional requirements. Okay, time for those deep dives. So we're going to go one by one through our non-functional requirements, expanding upon our high-level design for each of them until at the end we've satisfied all functional and all non-functional requirements, and we're getting hired and we're feeling really happy about our ultimate design. So we're going to start with the first one here, which is the most interesting for this problem, and that's strong consistency for bids. And so first let me introduce the intuition as to why our current high-level design doesn't satisfy this and what the problem with that is. And so let's imagine that we have a current auction where the maximum price is $10. And then we have two bids that come in, one right after the other. We have a $20 bid, and then we have a $15 bid. And so what should happen is that the $20 bid gets written to our database with the status of accepted, and the $15 bid gets written to our database with the status of rejected. But what could happen is the following. Let's imagine that the $20 bid came in, it read from our database saying what is the current maximum bid, and it got back 10. And then in the happy path, it would say I'm greater than 10, it would write to the database with the status of accepted. 15 would then come, read what is the current maximum price, it would read 20, it would then say, oh, I'm less than that, and it would issue a write with rejected. It's the happy path. But what happens if when this guy issues its read, it gets a 10, and then this guy issues its read before this one gets a chance to issue its write? And so this one issues a read and it also gets 10. And so what we end up with is something like this. And so the $20 issues its read, it gets a 10. The $15 issues its read, it gets a 10. The $20 issues its write with a status of accepted because 20 is greater than 10. And then the 15 issues a write with status accepted because it's greater than 10. And so the key insight here, or what's wrong, is that these read and write operations needed to be atomic. The read and the write from the $20 bid needed to complete before the start of the read for the $15 bid. And we need to ensure that this is always the case. So somehow we need to enforce this sort of ordering, in which case this would read 20 and life would be good. And so the fortunate thing is that these ACID compliant databases like Postgres enable this via something called transactions. You've probably heard of transactions. Transactions are simply there to ensure that a group of operations either all succeed or all fail. And so instead of saying read the current max and then write the new bid, we're going to read and write all in a single network request, all in a single transaction, and we're going to guarantee that it all completes together, or if something goes wrong, it all fails. And so let me show you what that might end up looking like. Here's some pseudocode for the transaction that we're describing. Here's some pseudocode for the transaction that we're describing. There we go. And so transactions in Postgres are denoted with this begin and commit. Everything between those two things are a transaction. And so in this case, we're going to query all bids for a given auction in order to find the maximum. And then we're going to write the new bid with a status of accepted or rejected based on whether or not that bid's price is greater than that maximum. And this can all happen via a transaction, so life is good. But while the transaction ensures that both 1 and 2 are guaranteed to both happen or neither happen, it does not ensure the serialization on its own. And so you could have this. Imagine that both of these happen at the same time. Well, we're going to guarantee that that read and write for, and say that this is our $20 and this is our 15. They get issued at the same time. Now, it's true that the read and write are going to happen in a single transaction, but we can still have that issue where that write happens, or before that write happens, this query or this read happens, and thus they both still get the 10. That problem that we were describing before. Right? So if these concurrent transactions happen at the same time, we can still have that concurrency problem, that interweaving of reads and writes that we were describing a moment ago. Transactions alone did not solve the problem, importantly. And so when I ask this question in system design interviews, oftentimes candidates go, okay, I'm just going to issue that via transaction. And this is right, you do need to issue it via transaction, but it's not alone for the reason that we're illustrating here. And so somehow we need some mechanism that's not only going to force the transaction, but it's going to force the serialization of these transactions, either this one first or that one first, right? Essentially, what we need to ensure is that while one of these is reading all of the bids, aggregating in order to find the current maximum bid, we're not allowing the other one to read until that write happens. We basically need to lock all of these bid rows. Don't read these until I release the lock and tell you that you can read them, because currently I'm reading them. That's essentially what we're saying here. And so what this would end up doing is looking something like this. We can use what's called a pessimistic lock. In Postgres, this is using the select update for syntax, but we're going to stick to the pseudocode for now because I think it's easier to understand. And so our transaction is going to look like the following. We're going to lock all of the bid rows for this auction, and then we're going to query all of the auction row, or all the bid rows, in order to get the max bid. We're going to write the new status with accepted or rejected, and then we're going to release the locks. And so then by a single transaction, the first thing we do in the transaction is grab the locks so nobody else is reading them, and then release the lock. And this makes sure that we force the serialization, because this could no longer happen, because only one of these can hold the lock at the same time. So if I come in next and there's already a lock held, well, by definition, then I'm going to have to wait until that lock is released for me to get it, and I've now forced the serialization, right? And so this is working, but it's not great. It's a bit of an anti-pattern, actually. Because with row locking, with pessimistic locking, you want to lock as few rows as possible, or else you could create unnecessary contention. And so as the auction grows and it receives hundreds or maybe even thousands of bids, locking every single bid row could become a major performance bottleneck. And so in our case, we're locking every bid row from a given auction in order to do this, and that's not great. So instead what we could do, and this is a little bit of a clever insight, is that we can quote unquote cache the maximum bid on the auction table. And then this way we only need to lock one row. We need to lock that auction row. And so let me show you what that might look like. So here we can cache the maximum bid. This is going to be the price of our current maximum bid. And now for a given transaction, we're going to lock the auction row, and then we're going to, let me just start over here, and then we're going to just read the max bid column. The nice thing here is no expensive aggregation too. So we're not holding the lock for longer than we need to. It's a single read of a column as opposed to reading all the bids and doing some aggregation in order to find the max. And then we can add the new bid row with status, and then we're going to update the max bid on the auction row if needed. So if this was higher, then we're going to come, then we're going to come and update this max bid to say 20 now. And then the last thing, of course, is to just release that lock, release the row lock. And so why is this better? Well, this is better because we're only locking a single row, just the auction row, and we're not locking it for longer than we have to. We're just locking it for a really quick read the max bid and be on your way, as opposed to having to query a bunch of different rows and do some aggregation. And so it drastically reduces lock contention, since we're only locking that single row, rather than potentially thousands of rows. And so great. At this point, this is an optimal solution. If a candidate in this interview told me that we were going to use transactions, but we also needed to ensure that there was serialization, and so we would use pessimistic locking. But instead of locking on the full bid table, or all bids for a given auction, we're just going to update our schema to have a max bid on the auction so that we only need to lock one row. And this will then force the serialization. Great. At this point, they've nailed it. Smashed it. I'm super happy as an interviewer. But I do want to quickly call out two alternative fantastic, maybe not as fantastic, depending on your perspective, up for debate, but two other alternatives here that could work. And so one thing is that instead of using pessimistic locking, you can use OCC, optimistic concurrency control. And so what happens in the case of optimistic concurrency control is that we don't take a lock at all. Maybe let me do a new one. We don't take a lock at all. There's no pessimistic locking. Instead, we just read that maximum bid column and we keep that around. And then at the end, before we update here, we would do the following. We would say, if the max bid is still the same as it was when we first read, then do this thing. Else, retry. And so what's happening here is that we're never grabbing a lock. We're reading the max bid column in the first place. We're seeing that it's $10. And then in the case of our contention with 15, if by the time we got here in order to update it, and we saw that it's no longer 15, but it's 20, then we know that somebody got in our way. We had an issue with concurrency here. And so all good, let's just redo our transaction. Let's start all over again. Read the max bid column is now 20, add the new bidder with its status of rejected, and so on and so forth, right? And so in this case, no locking, just optimistic concurrency control, where max bid is what's referred to as the version in optimistic concurrency control. And so when should you use this? When is one better? OCC is generally good when conflicts are rare, and thus the cost of occasionally retrying a transaction is less than the overhead of acquiring a lock for every transaction. And so it's really good in like read-heavy workflows where most operations don't conflict. You can make a really strong argument that that is the case here. You could also make an argument that there's a flurry of bids at the end of an auction and maybe it wouldn't be a good choice for OCC. The answer actually isn't what's important, it's the weighing of the trade-offs that would be interesting here. So that's another option, no pessimistic locking, optimistic concurrency control instead. Let me call this OCC, let me call this row locking. Now the other one, and this is a little bit fancy, but you can also just change Postgres's default isolation level to serializable. And so if you change, so just default isolation level, serializable. And so this is just a configuration in Postgres. You can just change your config to change the default isolation level, which is read committed, I believe. Don't quote me on that. But the default isolation level does not ensure that transactions happen in a serialized fashion. You can change it to serializable, and this is going to tell the database that every single transaction should appear as if it was executed one after another, not concurrently. And so Postgres is going to automatically detect these conflicts. It's going to force the conflicting transactions, to be aborted or retried. It's going to handle all of this for us. Now you might say that sounds great, and it is great. But what this means is that it's on the full database level. So now every single transaction is going to be serializable. Whereas with a large app like an online auction, there may be plenty of write workflows like when we create an auction and an item, for example, and we don't care about serialization, for which this would just slow us down because there's going to be a latency cost with the serialization. And if you don't need it for every single transaction, you probably don't want to enable it at the database level. So those are the options there. A couple other things just really quickly I want to call out, some bad answers that I always hear in interviews that are worth mentioning. The first one is that candidates realize with this problem, especially mid-level candidates, that they need some serialization. And so that's true, you need serialization, but they do it by introducing like a message queue here. And so they have all the bids come into a message queue, they pull them off one by one in order to ensure that we process the full $20 before we move on to the 15. The intuition is good here, you need serialization. Message queue is actually not bad in terms of fault tolerance and durability, but it is bad in this case in order to force the serialization for the reasons that we just showed. There are a lot of solutions native to the database management system that will handle this for you. And so this is basically just taking what's already done for you in a database and extracting it and kind of building, you could say a worse, less efficient version. So that's one option that's bad. The other one is that instead of using row locking, people add Redis here and do a distributed lock. And I fault myself a little bit here. This is probably because people are misunderstanding the guidance in Ticketmaster, for example. But what they end up doing is that they end up locking on an auction, doing the write and the read, and then unlocking so that the 15 can grab the lock, do the write, read, and so on. And so they lock here with some TTL of like 1 second. Now, of course, the consequence would be that you're locking this thing for far longer than you need to. I hear many candidates even tell me 5 seconds, 10 seconds. We don't need that much time to issue a single write, read, and a write. That's like milliseconds. And so if you had 100 requests all come in at the end, and this was only a 1 second lock time, then the 100th request is going to happen after 100 seconds. And so a user is not going to know whether their bid was accepted or rejected for 100 seconds. And also the HTTP connection will be long closed by then anyway, so you couldn't tell them regardless. And so what this is doing is that this is basically, instead of using a native database lock, which could handle this for you, locking for the length of a transaction, you're adding an additional distributed component in order to handle this, which is completely unnecessary and suboptimal and bad. So don't do that. The only time that you want to use a distributed lock is if for some reason you need to lock for longer than the duration of a given transaction. So like in Ticketmaster, we need to lock for 10 minutes. You can't hold a pessimistic lock for 10 minutes. At least you shouldn't. It's going to create a bunch of contention. And so that's where distributed lock might make sense. In the cases where you need to lock for longer than a transaction, and there's really high write throughput. That's another important consideration. There's really high write throughput, so an in-memory distributed lock could be great. But in this case, no queues, no distributed locks, handle everything within our ACID-compliant Postgres database, which is great at all of these things. All right, so we have the first deep dive in. Let's come over then and take a look at what our second is. And that's what we want to talk about, fault tolerance. Specifically that we don't want to drop any bids, especially when people are willing to pay money for something. Fault tolerance is usually particularly important. And so if we come back over to our design, let's talk about what the concern would be. And the concern would be that we have this bid service here, and as a bunch of bids, a flurry of bids maybe come in at the end of an auction, then this bid service could become overloaded, either via CPU or memory, and could go down. And then in the time that it goes down, we're bringing other ones up, but we're dropping bids at that moment. And that would be really bad. And so what you could do is just over provision the hell out of it. Like we could just scale this horizontally such that we know it'll never go down. But then we're just paying a bunch of money for all of these expensive servers that we don't actually need in the majority of cases. And so the best fix here, the most elegant and common solution, is to introduce a durable message queue. And so what that would look like is the following. We can put a queue here, maybe like Kafka, for example. And then we can put a really lightweight producer here. This is just a server. And so this producer's needs to be single direction. This producer or this server's single responsibility is to take an incoming request to create a new bid and to put it onto Kafka. And so this is nice because it has very little responsibility, meaning it's really cheap. Like this can be a cheap server with not a lot of CPU, with not a lot of memory. And thus, it's the thing that we can over provision like crazy because we can afford to. It's not an expensive server. We're just going to create a ton of these so that when a spike comes in, these can handle it and immediately get it onto the persistent message queue. And then our bid service can be pulling off of that persistent message queue one by one whenever it's ready to actually process the bids. And so whether these go down or under provisioned or otherwise, whenever they're ready, they're just going to pull off this queue. You can think of it like writing your name on a waiting list at a restaurant. So even if the host goes and takes a break, our bid service here takes a break, your place in line is secured. We're going to come back here. Your bid was never dropped. We're going to process the bid and get it into the database. And so any persistent message queue would work here. I chose Kafka, SQS, otherwise all good as well. Now, the interesting downside and the consequence that most candidates, especially most mid-level, even many senior candidates, don't realize when they introduce the message queues here for durability is that they've now made their process asynchronous. And so now this create bid request is async, which means that we can't directly respond to that HTTP request with the accepted or rejected. And so now a user is going to issue their new bid. They're going to get back a 200. Yeah, I got it. But they're not going to know whether their bid was accepted or rejected. And so in order to solve this, we now need to have more persistent communication between the client and the server, which transitions us pretty nicely into our next non-functional requirement, which is those real-time client updates. And so how can the client get real-time updates about the bid history, including now knowing whether its own bids were accepted or rejected? And so the first easy thing that you could do is you could have something like an additional endpoint, or just be calling this endpoint that we have, view auctions, over and over and over again. And so this would be polling. Kind of similar to if you guys have watched the leak code video, we issue our code to leak code. It runs all of this asynchronous processing in order to run that code. And we're just simply polling leak code every 5 seconds to know if that's ready so that we can tell then on the client that it was accepted or rejected. So that's option one, basic polling. In this case, unlike with leak code, it's not a great solution. It's a bit resource intensive. You're going to always constantly be polling for new bids to come in. And the timeliness of the bids really matters here. Unlike leak code, if I found out 2 seconds later that my submission was succeeded or rejected, it doesn't really matter. But here, I want to know the auction might be ending and I want to make sure I put in a higher bid. Or I want to know what everyone else is bidding exactly in real time as they're bidding it, so I know what I need to bid. And so the right solution here is to open up a more persistent connection. Polling, even long polling, where we keep the request response period open longer than just a couple seconds. The polling solutions aren't great. Instead, we want to open up a persistent connection. And that would be either a WebSocket or SSE. And in our case, we're going to opt for SSE because it's unidirectional. Relative to WebSockets, it's more lightweight. It goes over HTTP instead of having its own protocol, and it's supported by most modern browsers. We have some great breakdowns on the site and real-time updates about the differences between those two that I recommend you read. But the essence here is that whenever a new bid comes in, as soon as it's written, accepted or rejected, if it was accepted, and in this case to notify a client, maybe even if it was rejected, we're going to push it over SSE to the clients. And so this way the clients have a real-time feed coming in of all bids as they're showing up. They get real-time updates. A bid comes in, we put it onto Kafka, the bid service pulls it off, it pushes it to all clients, or maybe I should invert the order. It first writes to the database, gets confirmation of that writing to the database, and then pushes it to all clients. And so if you're sitting there and you're a client, you're seeing bids just show up on your screen, and you know the bid history in real time, so you know exactly what you need to bid. Awesome. So this way we solve the asynchronous part here, because we're going to push over whether your bid was accepted or rejected, and then you on the client know your own ID. And so you can maybe highlight client side to the user your particular bid in some, maybe making it bold or colored or otherwise. But you'll get to see your bids and everyone else's bids, which is great. And so then we come to scale. And so the first thing that I want to talk about with scale is this bid service and the SSE connection. And so if you've watched, WhatsApp or, live comments, where else do we use it? Any place where we use this pattern with SSE or any real-time communication. In order to scale it, we have two options. Either we have some dispatcher, like using Zookeeper or otherwise, in order to know which of these to push it over to, or we have PubSub, which is the most popular and maybe the one that I recommend you use in an interview because I think it's the cleanest to describe. But let me just be clear about what the problem is here first. Imagine that we scaled this because we need to support 10 million concurrent auctions. And so we have a bunch of these different bid services. And now we have a user who's connected to this bid service 1, and he's listening to auction 1. But then a new bid comes in for auction 1 and it lands on this bid service. And so this bid service writes it to the database, and then this bid service says, okay, let me push now over SSE any updates to anyone listening to auction 1. And it does that. Let's assume there are some. But this guy never got that update because he's not connected to this bid service. He's connected to a different bid service. So somehow we need these bid services to be able to communicate with each other. This bid service needs to tell this one, hey, I have a new bid for auction 1. I know you have someone who cares about auction 1, so you need to push this over SSE for them. And so the solution that we go into in detail in those other videos more, but I'll talk about briefly here, is PubSub. And so you're going to introduce some PubSub such that you can broadcast. Think of it like a megaphone. This bid service can yell into the megaphone, hey, all other bid services, I have a new bid for auction 1. If that's something you care about, you should know. And then all other bid services are just listening to that megaphone and taking that information and acting accordingly. And so what this would look like is that you're publishing to PubSub when a new bid comes in. So a new bid comes in. And then at the same time, everybody is listening. So you're listening for bids you care about. And the bids you care about would be the bids on auctions for which you have connected users. And so in memory on each of these, or maybe let me just take a step back and kind of talk about the full flow here. A client opens a new auction on their device, at which point they're going to make a request to connect over SSE. We're going to tell them the device they need to connect to. Maybe it's this one or the server they need to connect to. And they're going to initiate this connection, and the connection is going to be created. At the same time, they're going to tell then, in that initiation of the connection, this server, the auction that they're listening to. And so this server is going to put in memory some mapping like this. Auction 1, I care then about SSE connection 1, right? And so now when a bid comes in, we're going to put it on PubSub, broadcast it to everybody. And in the case where it is a bid for auction 1, then this guy is going to look in its internal in-memory mapping and say, hey, I care about auction 1. I have one SSE connection that cares about that. And so it's going to iterate over this loop. Maybe we could even say there's more, just for an illustrative example. It's going to iterate over that loop, and it's just going to call SSE connection 1.send with that bid. And it's going to send that to each of those two respectively. Right? So again, we go into more detail on that in some of the other videos. I don't want to be redundant here. And in this particular interview, this isn't the place where you would go into all that much more depth here. And so that's kind of a useful aside for me to say. In this interview, the depth here was on durability. It was here on scaling. It was on the consistency components. And then there are some other additional follow-ups which I put in the write-up, which interviewers sometimes like to ask. But in any case, you want a full, complete picture of the total aggregate amount of depth. It doesn't mean that you're going to be able to go fully deep in all 3 of those things that we just did in the limited amount of time. Instead, you're probably going to go fully deep here because it's the most important. Maybe you go like 50 to 70% deep here and like 30% deep here. And then the total depth is thus enough for your particular level, right? And that would obviously depend on the level that you're interviewing for, but hopefully that's clear. Okay, before I sidetrack too much, we're still on scale here. A couple other things that I would look at in terms of scale is I would just look at each of my components. We talked about scaling this one up. We talked about scaling here. In Kafka here, we would want to partition by auction ID. That makes sense because that's where we want to enforce ordering anyway. And so we could partition by auction ID. You might get the argument that like, what happens if there's tons of bids for a particular auction? You have a hot auction. I would push back on my interviewer and I would say that's not going to happen. And the reason that that's not going to happen is because each subsequent bid costs more money. And as things cost more money, almost by definition, it means less people can afford it and thus less people are bidding. And so could we get an influx of thousands, tens of thousands of bids for a given auction at the end? Of course we could. Kafka partition can handle that, no problem. If we were talking about hundreds of thousands, more than that, millions, then we would want to talk about some celebrity problem and further partitioning a given auction. But I would push back on my interviewer and say that I'm not worried about that. I'm not worried about there being that much throughput in this case by the definition of the problem. So auction service, we can horizontally scale this as needed. It's stateless, so no big deal. And then our database here, maybe this is a place where you would do some math in order to say I have something like 10 million auctions. Each of this, if we round up, is maybe, this is a high estimate, but let's say a kilobyte of data. And then for each of those 10 million auctions, on average, maybe there's 100 bids. Each of those bids is maybe 200 bytes. You can end up doing this math, and you're going to find out that it's actually not a lot of data. So it could probably fit on 1, 2 instances. If you did, though, want to shard this up, then no problem. Beyond just read replicas, which could help with the read throughput, if you wanted to end up sharding here for writes, which I don't see here being a problem, but your interviewer might push you on it, then you would probably want to shard on auction ID. And the reason that you would want to do that is because you want to make sure that the bids for a given auction in the auction row exist on the same shard so that you can issue that transaction. That's really key. So if you ended up sharding such that your auction and bid were not in the same table, then you would now be dealing with distributed transactions, and that whole conversation that we had over here is largely mute. So just make sure that those end up on the same device. And there you have it. We built up our high-level design to satisfy those functional requirements. We layered in our non-functional requirements, expanding on our design through our deep dives, and now we have a well-designed auction system that should satisfy your interviewer. Hope you learned something, and thanks for being a premium user.